Hi, and welcome to the sixth section of this course, Convolutional Neural Networks. The section will demonstrate the following topics: Origin of Convolutional Neural Networks, Applying Convolution in TensorFlow, Subsampling Operation, Pooling, Improving Efficiency, Dropout Operation, Convolutional Type Layer Building Methods, MNIST Digit Classification, Image Classification with the CIFAR10 dataset. Now, we will see the first video of Section 6, Origin of Convolutional Neural Networks. In this video, we will learn about few topics, that is, getting started with convolutional, kernels and convolutions, interpretation of the convolutional, continuous convolution. The original use of this function comes from the 18th century and can be expressed in the original application context as an operation that blends two functions occurring on time. Mathematically, it is defined here. When we try to conceptualize this operation as an algorithm, the preceding equation can be explained here. Flip the signal. This is the part of the variable. Shift it. This is given by the tau summing factor for g, open bracket, tau, close bracket. Multiply it. This is the product of f and g. Integrate the resulting curve. This is the less intuitive part because each instantaneous value is the result of an integral. Discrete convolution. The convolution can be translated into a discrete domain and described in discrete terms for discrete functions. Kernels and convolutions. When applying the concept of convolution in the discrete domain, kernels are used quite frequently. Kernels can be defined as NXM dimensional matrices, which are normally a few elements long in all dimensions, and usually m equals n. The convolution operation consists of multiplying the corresponding pixels with the kernel one pixel at a time, and summing the values for the purpose of assigning that value to the central pixel. The same operation will then be applied, shifting the convolution matrix to the left until all possible pixels are visited. In this example, we have an image of many pixels and a kernel size of 3 × 3, which is particularly common in image processing. Interpretation of the convolution operations. Having reviewed the main characteristics of the convolution operation for continuous and discrete fields, let's now look at the use of this operation in machine learning. The convolution kernels highlight or hide patterns. Depending on the trained parameters, we can begin to discover parameters such as orientation and edges in different dimensions. We may also cover some unwanted details or outliers by means such as blurring kernels. As Lacan in his fundamental paper stated, convolutional networks can be seen as synthesizing their own feature extractor. This characteristic of convolutional neural networks is the main advantage over previous data processing techniques. We can determine with great flexibility the primary components of a determined dataset and represent further samples as a combination of these basic building blocks. Nice! We've successfully learned about origin of convolutional neural networks.